This is 4.6, modeling exponential functions. We've already talked about logarithms and how to solve equations with logarithms. Now we're going to put some application to it. So the first thing is exponential growth. We already talked about exponential growth functions. Remember, when you graph exponential growth functions, they're literally going to start off really tiny and then they'll grow exponentially. And we already talked about the base of that. The base has to be bigger than 1. So it might be 7.3 to the x power, something like that. And that's exponential growth functions. And specifically like the population of New York City or Los Angeles or the population of a bacteria. So we use exponential growth functions as that illustration. Now, specifically doubling time. So now we're talking about a specific type of exponential growth. When it doubles, notice the base is 2 automatically. Notice also A is the doubling time, how long it takes to double. Okay, and then NO is the initial size of the population, like the population of the bacteria. So let's look at an illustration. So here's bacteria doubles every 3 hours. So again, doubles every 3 hours. Again, the word double should tell you that the base is 2. And we know we have T over 3 because it's doubling every 3 hours. And the initial bacteria is 1,000. So we're going to multiply it by 1,000. So that's how we're going to be setting this up. Notice that is the formula in sub t. So that's the function that I'm going to be using. And then we're going to see how many bacteria grow after 15 hours. So we're literally just going to substitute 15 in. Which is 2 to the 5th. And then we're just going to calculate that, which would end up being 32,000. So how many bacteria after 15 hours? If it doubles every 3 hours, well, it's 32,000. So how many hours until bacteria reaches 100,000? So if we know it's going to reach 100,000, so what we're trying to find is when it will reach that, how many hours have taken place since that. So remember the function that we have is this. So we're solving for t. Well, dividing by 1,000, we're going to get this. Now, once you get it to this, there's a couple of ways to solve it. You can put it in log form, or you can just literally log both sides of this. So if we take the log of 100 and the log of 2 to the T3. Again, you can do it this way, or you can write it in, notice this is actually exponential format, so you can actually just write it in log format as well. So either way, one of these ways to work it is totally up to you. So this right here, log, remember, if it doesn't say a base, it's automatically 10. So this is automatically, log of 100 is 2. And remember the exponential, the log rule with whenever you have an exponent, so the t divided by 3 comes out front. And then what you're going to do is divide both sides by log. So this literally goes to 2 over log of 3, log of 2. And then just multiply by 3. And you're going to get approximately 9.93. So it takes about 20 hours. So if we rounded, it would be about 20 hours before the population of the bacteria reaches 100,000. So let's look at another possible scenario. If we talk about exponential relative growth, so notice here we got the same type of problem, but notice the E is there as the base. And notice that it's, again, if I say exponent has a relative growth, so you want to switch gears from doubling time to this. So here the initial is 500, and we're multiplying that by E. The rate is 40%, so 0.4 t. So that's my function that I'm going to be using. And then it wants to know specifically 10 hours. So we're going to substitute this in 10. And then all we have to do is just simply calculate that. And that's going to give us 27,300. Now, the next part B, hours until it reaches 80,000 bacteria. So notice we've already found out after 10 hours it reaches that. So we want to find out how many hours will take place until it gets to 80,000. So here we're going to have 80,000 equal, remember the function that we found up here. And then we're just going to solve this. So this is going to be e to the 0.4t equals 160. I divided both sides by 500. And then you're going to ln. Remember how to get rid of an e? You're going to ln both sides. So literally we're going to have ln of 160 equals 0.4t, which means t is approximately 12.68, or, you know, and again, that's how many hours approximately, so 12.7 hours. 12.68 hours until it reaches 80,000 bacteria. All right, so let's finally talk about Newton's law of cooling. So here we have a formula that you need to pay attention to. So this is T of S, T sub S is the temperature of the surroundings. And D of 0 is the initial temperature difference. Pay attention to the difference. And then the K is some constant. So a scenario is like a cup of coffee, or a turkey, or with forensics, like a dead body or something. You know, there's many different scenarios when you talk about, you know, when you take a certain temperature of a cup of coffee, let's say, and you set it out in room temperature. In 10 minutes later, you know, 15 minutes later, what's the temperature of the coffee? Or the same with the turkey, or, you know, whatever we're talking about. Or again, with forensic, talking about you know, a body that's been, you know, dead for a certain amount of time. They can calculate, you know, how long it's been, or the body based on the body temperature with the time of death that it took place. So let's look at some illustrations here, just using Newton's law of cooling. So here you have a cup of coffee with the initial temperature of 200 degrees in a 70-degree room. And then 10 minutes later, the temperature is 150. So first, let's find the function, and then we're going to find the temperature after 15 minutes, and then we're going to find the time until the coffee is cooled down to 100 degrees. All right, so notice, first of all, using this function, this formula. So notice what we have here. We have 70 degrees is the room temperature. So that's what we're starting at, T of S, 70 degrees. Now, the initial difference temperature, that's something you got to pay attention to, because notice it's going to be 130. Because notice that the cup of coffee originally started at 200 and it's going into a room of 70 degrees, and then the rest of it is e to the negative kt. So this is what the function I'm going to start with here. And I notice I haven't used all the information. It says I have not used this right here, that piece of information. And so what I'm going to do now is I want to find what K is. K is the constant. You know, if we're talking about coffee, we're talking about ice cream, or a turkey that comes out of the oven, whatever it is, the K, depending on the substance that we're talking about, that's what K is. It's a certain constant depending on the substance. So we need to find out what this is. And obviously, we're going to use 10 minutes for the time. So we have 70 degrees. And we know the temperature is going to be 150 degrees. The initial was 70, so 130 E. And we know it's 10 minutes later, so we're going to put negative 10 K here. So I'm trying to find this for K. So once we start solving this, And then again, when you get to E, to get rid of an E, you're going to ln both sides. Which means K is approximately 0.04855. So that means our function that we're trying to, for this entire problem, what we want to do is we're going to basically rewrite this, but now we found K. Now, something I do want to point out, we found K, but notice the formula says it's a negative, so make sure you put that negative in there as well. All right, so that right there is the function that we're going to use for any type of temperature. So if I want to find the temperature of the coffee after 5 minutes or 10 minutes, 30 minutes, whatever it is, I can use this formula to be able to do that. So it says 15 minutes. So that by the way, that's all of part A. So part B says after 15 minutes. So we're just going to literally find after 15 minutes. We're going to plug 15 into this problem. All right, and then once we just plug that into the calculator, we're going to get 133 degrees. So the temperature of the coffee after 15 minutes is down to 133 degrees. So, and then finally, letter C, what is the time that it takes until the coffee is down to 100 degrees? So how long would the coffee be sitting there until it finally cools down to 100 degrees? So we're going to put 100 degrees. We want to find out when the temperature is going to equal 100. So we're just going to solve this equation. So if we subtract 70, we're going to get 30 here. Divide by 130 on both sides. And then again, every time you see an E, to get rid of that, we're going to ln both sides. So here we have ln. And then T, once you divide both sides by the negative 0.04855, you're going to get approximately 30.2 at the time. So after 30.2 minutes later, the coffee is down to 100 degrees. And that's how you use Newton's law of cooling.